Prog Sweden. Welcome to this first meetup. When we started it in November, me, Matthias, and John in the back were like, hope someone comes. So there's a few people here, very cool. Super happy for that. Agenda today, intro, and then first presentation is data efficiency on Beam. Choose the right data representation by Dmytro. I'm not going to go for the last name. Yeah, Dmytro, sorry. And second presentation, how we write Haskell for production at Klarna by Felix. And then some more mingle. And then please, someone ask if you have to pay for the beer. No, you don't. Have to pay for the beer? Take beer. And there's still, I think there's still sandwiches up there, so take them too. Yes, this is the community. We love functional programming. We try to be open and inclusive here. We like to share. That's most important. I started to work actually with functional programming in Erlang in 2008-9. It's let's spread this more. When I started, there was nothing. There was an obscure company called Creditor and Ericsson. Today it's much more, but let's spread it more, so more programmers start to work with functional, because then more companies will use that. Also, we would like to thank Adabit. I'm representing Adabit, so we're paying for this. Last but not least, we want to run more meetups, of course. So if you have anything you want, I want to talk at the meetup, I have anything I want to present, I have a friend that should present this cool stuff, reach out to us. If you have a venue, please also reach out to us. If you have somewhere we could host a meetup. Yeah. So just contact me, Matthias in the front here, or Tim in the back. That's it. That's it for me. Do you want to start, Dmytro?
Yeah. Hello?
Yeah.
Sounds good. Where's my slide deck? Is there a way to see this presenter notes? Yeah. Stay away from moving the mouse too much. Who needs the notes? I know it anyway. Alright. So this talk is called Data Efficiency on Beam. I welcome everyone. And I'm glad that you chose my talk to hear it, and hope it will be useful. My name is Dmytro Lytovchenko. I work here in Stockholm for Erlang Solutions, and we are hiring, so you're welcome. You will be able to find more details if you want. This is the mandatory picture of last year's ecosystem, and not much changed. It's still same languages, all built on Erlang on DP, and everything is running on Beam. Beam is the virtual machine that runs all of them together, and everyone is happy in this ecosystem. And it scales, it grows, it runs in parallel, it uses all your processor cores, 80, 128, how many have you, everything will be consumed. Yeah, well, you have to limit, it will consume everything literally. You have to tell it slow down, not too many cores. So let's begin, just a quick information. When you create a program and compile it, be it Elixir or be it Erlang, doesn't matter, the product of your build is a Beam file. It's a simple binary file. If you want to read it, you can find some information. I will not go into much details. What is interesting for us is that it contains the code that you can inspect. There are tools for it. And it also contains a literal table. So everything you put in your source file, your arrays, your literal dictionaries, trees, nested data, maps, everything is compiled and placed into this literal table. when you access something from the literal table in your code, it is cheap and instant. No data is built, it is ready. So you can build lookup tables, you can build, if you want to, for example, create random addresses and usernames and last names and everything, you make lookup tables in your source and then access them. It will go to this literal table instantly, very cheap, no extra costs. But during code upgrade, this might be copied. It doesn't matter, it works transparently. You don't need to think about it unless you reload code very much. Now, to terms. Term is a general name for any data value in the Beam virtual machine. It is any value in Elixir, it is any value in Erlang. It is all together named term. Internally, in virtual machine and in memory, all terms are stored as a machine word. That's 64-bit integer that fits into machine register, so it's most efficient. And as well, process memory also consists of words. So in the following slides, I will mention words. So everything in virtual machine is measured in words. All words have to be reserved right here at the least significant bits. So you never can use more than 62 bits for a number. That's the limitation you may sometimes observe when you program. And I will mention it later when we come to integers and atoms as well. So these 2 bits can be 4 different values, and 2 of them are what we're looking at them now, and it can be immediate value. So I don't remember exact bit values, it doesn't matter, it's constant since it's source, you never see them. So it can be immediate value. So it means that if 2 of these bits have special value like 0, 1 or something, so then the rest of them is an integer, or rest of them is the bit process ID, or something else. And the other 2 could probably 2 zeros, I don't remember again, but it can be a pointer. The rest of it is a pointer to memory. So what's good in this is that we can use 62 bits to store something. Or we can point to an object in memory. And we will look what are the tuples, how they look in memory, we will look how lists look in memory, and how it's useful for you. When you plan your data, you plan your data structures, you plan for performance, or you plan for compact memory usage. A memory of a process, when you program, is just an array of words, of terms. So anything you place in memory is array, so that part is simple. Your stack that you see in the programming books and you see in documentation, they mention stack. What is stack? It's another array which grows in opposite direction. Again, simple, there are no special structures on array, just array. All the registers in virtual machine that are used to pass parameters to functions, they are also terms. Again, when you store something here, when you store a tuple, it's just an array. If you need to modify it, you build another one with new values. If you store a list, so each cell, each element of a list is a cell, is a linked list object with a value and a pointer to next. That is called list cell, back from Lisp times, when it was called cell for the first time ever. Maybe it was called before, I don't know, the history before Lisp. Alright. If you store a binary, it goes into array of words. Even if binary is a bit string and is incomplete, so you store 7 bytes or you store 17 bytes, the rest will be unused, probably bad by zeros, and so on. So it's stored as array of words. And if you store a float, and that's a terrible way to store data in Beam virtual machine, the float will be stored as a header word and your float. That's 2 words on the heap. And in 32-bit machines, it will be slightly more complicated because you need 2 32-bit words to store a double. So immediate values. If I quickly scroll back to this slide, the term, any value in your virtual machine that is an immediate, so these bits indicate that it's immediate, it can store any simple data that fits into 60 bits. And these two more bits define what it is. So there is even, because we have more types than just 4, so one of them defines that we should look into more bits, so we have immediate 2 value. That limits the remaining, the tail of the value to 58 bits or 26 and 32-bit machines. So that immediate value you can store small integers that fit into these bits. They can store local bits and ports. They can store atoms. Atoms go into immediate 2, so they are limited to 26 bits. So that is 32 million or something to the power 26. Yeah, well, or 64 million, that's the atom limit. And on 64-bit machines, because of this all 32-bit limitations on 64-bit machines, it is still 26-bit limit for atom table. So you can never ever exceed 64 million atoms. And therefore you should not create so many atoms in runtime and be super careful, because it crushes your virtual machine. As well as nil, that is a special value for empty list in the virtual machine. It is an immediate value. It does not pointer to memory with empty list. It is a special value. And some internal values also use this format to store what virtual machine needs for try and catch. What's important here for us is that, well, this is not the same as elixir nil, because elixir nil is just an atom. It's not a special value. Elixir has empty list that is represented as nil in virtual machine, special value on the left. If you store something in a list, and it's again, I would try to mention elixir on every slide, but it is the same. Elixir and Erlang, these languages store lists in the same way. Your value which you store in your data structures is this pointer, is a single word which pointers somewhere to memory, where you have your first list element. First list element will pointer to next list element, and next list element will possibly have a tail. So this defines a list of 0, 1 and empty tail. That is properly formed list. So list cell is always 2 words. If I would be going through the memory, I would have no idea if this is 2 separate values or a list cell. So this is the minimal structure that you can have in a virtual machine, a list of 1 element and the tail. It uses just 2 words of memory. And anything, any list term, the value is any value that you store in your program is a pointer to memory. Only empty list has special value. So last element of a list may be a nil, that is possibility. The list which has last element as a nil is called proper list. So if you store the list, 1 element in the list with an empty tail, that becomes 1 list cell, that is just 2 words of memory you use. If you create a list of 2 elements with 0 and 1, it will create 2 cells, like on this entire picture. This will use 2 cells or 8 words of memory. There is a trick to minimize this, but this is how lists are. Lists are just linked lists, forward linked lists, if you remember your C programming course or data structures programming course. Lists are just forward linked lists. What good are lists? They can only iterate forward. This is very fast, this is very cheap, this is good for your program, but you cannot iterate backwards because it's forward linked list, and it's also very cheap to prepend because you just built another cell on top. And you prepend. As long as you want, you can prepend elements. No memory is moved, only new list cells are created. One nice trick. If you need to store just 2 values in a structure, you store the second value as list tail. In this way, the first cell becomes your first element, and second cell, which is tail, becomes your second element, which creates an improper list. It's not list anymore. But it stores two values. It only takes 2 words of memory. And this is the most efficient way to store two values in Erlang and Elixir. If you try to store it as a tuple, it will use 1 extra word plus your data. That's 3 words. If you try to store it as a simple list, like this, it will use 4 words. That is first cell, second cell, including tail. Like this. This is the least efficient way to store two values. And this is the most efficient. You just put it like head, bar, tail. You can see it in some code bases which store millions of records or hundreds of millions, and they of course they had to save memory because 1 extra word times several millions becomes something you should try and optimize. Again, if you try to build something in a list, so prepending is the cheapest way to do it. If you want it in the opposite direction, it's always better to prepend entire thing in reverse and then call list reverse. This is still a copy, but it's quite efficient. There are tricks and optimizations to make it cheap. So if you have to, you build it in reverse and then call list reverse. That is better than appending to a list, which is much more expensive operation. It is quadratic complexity. And then if you take part of a list and build a new list, it's very cheap again, because it counts as prepending. You can reuse parts of list, build other lists, and other lists together, and the memory is not modified. You just take pieces and build something new. That is cheap. And list comprehensions can be optimized. That is compiler trick. You don't need to remember it. It will try to do better for you. So don't worry if you build a list comprehension and something in it is created and the result is ignored. It will be smart and not pollute the memory. What you should not do with lists. Length operation on list is a full iteration. It will not store the data, the list size. It will have to count it every time. You do not want to call list length too many times. Also, nth element is quite expensive in the same way. If you do minus minus operation, it is n times m complexity, but in modern OTP, like starting from version 20, it has been slightly improved. There are better algorithms used. Oh, 22, not 20. And plus plus is again complex because to append something list to a list, the first part has to be rebuilt because we modify the tail so it contains the rest. So the first part will be copied and the rest will be cheaply appended. So on the left list is complexity. If you need to do plus plus, then place the shorter list on the left. In that case, it will be very fast. And then if you do flatten or reverse, that will be a full copy, which is sometimes what you want, and sometimes you don't want it. So remember, it will be a full copy. Yeah. When you build a list, that's just programming 101. Don't do recursive calls with growing new stack, but you want to take recurse to not crash your virtual machine or not crash your process with Stack Overflow. Okay, IO lists. That's a special case of a list. Again, they exist in both Elixir and they exist in Erlang. It's just lists nested in lists, and you can also store single atoms, I think, also are accepted. You can store strings in lists, you can store lists of lists and empty lists. It all goes together in a mishmash, and it will work. Many library functions accept this kind of structures. And it is much cheaper to build such structure when you format, for example, a template. You need to put a header, a footer, then some variables are substituted, and then you replace something, and so on and so on. And then you build this kind of structure. If you need to prepend, you put it in front, build a new list, it just grows in depth, it's happening quite fast, it's very optimal. And what's good to it is that many functions in standard library will take this and use it for sockets, for file operations, for printing, you can use this kind of lists. So if you build any big string, just remember it's very good, it's fast. Again, well, prepend and append very cheap, and it is fast. Yeah, so when you need to append something to such a list structure, you just build a new cell with the head and tail. If you need to prepend, you just build a list cell with your head and append something. You can again build list of several elements together, and it replaces plus plus and list append. And that's what I mentioned, many functions accept IO lists. This is, you don't have to convert, you don't have to flood them to write it to a file or send to socket. So just build it and off it goes. It is good for your performance. It is also good for your memory. You don't have to copy to build a longer string. You just build 2 pieces and send it. Again, where was I? A term. A term can also be that we had a quick look at immediate values. They are just words. You don't need to think about them. They cannot be any smaller. And we looked at list cells. It also can be a pointer to a box. Box is everything else that does not fit in one word. So all the data types that we have, like external bits with node name in them, or ports with node and something in them, or lists again, but lists have special type. Again, tuples, maps, all the kind of data that we store in memory that is big, it's stored as a box value. So what is good in them is, let's see. Yeah, so again, it's your value that you store in your structures. It's just a pointer to a box. That can be binary, floats. Again, float goes here. Tuples goes as array here. Maps, refs, bits, ports, big integers. If your integer does not fit those 60 bits, it also goes into the box. And function closures that you create, function pointers, references, exports, it all goes into a box. And it's just a few more words allocated on the heap, and it's stored there. If you can avoid this transformation, if you, for example, you had a counter in the table, and it was integer key, and it grows, and you grow over 28 bits on a 32-bit machine, then you hit the short integer limit, and it is converted into a big integer. It immediately blows up your table size and your index size, and everything in memory increases, because from that point, your integer will be a box with big integer in it. So that's something to remember when you investigate, like, why my memory just exploded. Because your counter is now big, and you have a million of those counters. So something like this, yeah. So just remember your limits. When your bit size in the immediate value is exceeded, then it will be created into a box, and bigger value will be stored here. So all boxes always have one extra word of memory for explaining what it is. So if you store a tuple, it will be header mark in a tuple, rest bits will be size, and there your array of data. So if you store 2 values in a tuple, that will be 2 values plus a word of extra memory used. So now to the tuples. I just explained everything. Yes, a tuple is a box. It has a header, it has your values, and it's very simple. It is read-only. So if you create a tuple or an Erlang record, it is not the same as Elixir record, because Elixir records are maps. In Erlang, if you create a record, it also will be a tuple, and it also will be read-only. If you modify it, the entire thing will be copied in memory, the whole thing will be later destroyed, and things you want to modify also will be copied and placed there. There's always one header overhead, and the size of tuple is limited, again for compatibility reasons, because we just used 6 bits to mark its type, and 32-bit word on 32-bit machine. What's left is 26 bits here. That is the limit that is imposed on tuples. You cannot create a tuple longer than 64 million or 67 million in decimal. Yeah, 6 to power 26. So it's just a simple array. How is good? It is very cheap to access. So you store in tuples things you need to look up by index number. These are just arrays. So if you need to look up something randomly, I don't have other example than building a random name from a list of last names, first names, and street names, but it's an amazing example. I had it hard-coded in a source file, and it worked very fast. It's good. So yeah, lookup is very cheap. And if you have literal tuple, it's also cheap, but you can build it and then convert from list to tuple once, pay the performance cost, and then look it up from a tuple because it's array. And there are some optimizations that compiler can do for you when it sees you building tuple, like set element 0, set element 1, set element 2, and so on. It will observe it and optimize for you. You don't need to think about it. Otherwise, if you do a big operation on a tuple, consider making a list first and then doing something, then converting back. Now maps. Maps are a new type from Erlang 17, that's been some years ago, so it's not new anymore. But if you program Elixir, every record is also a map, Erlang map. So you need to consider the performance limitations. If you use Elixir records and you store millions of them, then these limits may as well create trouble for you, like memory consumption or performance. So map again, map is a box. Because it does not fit in one word, we pointer to memory and we store things that are in the map. It can be a sorted pair list if it is fairly small. That's compact, it is quite fast. It's also simple to implement if you are programming something like you want to create your map in C or C++. And when it grows big, it is changed into a hash array map trie implementation. And in that case, it can grow bigger. It is faster to look up on bigger trees. But on small, it's not worth it. So this is the limit of the 32 keys. It becomes this. So it is not efficient if you have very big structures with more than 32 keys, or like 50 or 60 or 70, and you have a lot of them. So for each map, the structure will be created. It is many, many words of memory, and it's not efficient. But it's actually the price. So know your limits. If you need to store it in a more compact way, consider not using maps, but use some simpler structures like tuples, property lists, or just key value pairs. So lookup in a map is faster because it is sorted. If you need to find, if it's still stored like this, and you look up it, so binary search is quite fast. But when you go into a tree, it's slow, but it's still faster than other data structures. Now binaries. Binaries, they might look simple in your source code, because you just store some bytes. But internally, binaries can be like 1, 2, 3, 4 different types, and there is even one extra type. So what is happening, in fact, when you create a large binary that is very large, like more than 64 bytes, something that came from internet in a socket, or user submitted a file or something big, then it is copied to a separate memory area called binary heap, and a small reference is created that you operate. So the entire thing is not moved when you send your binary between processes. It came from socket, it comes to socket handler or to web handler, then you process, do something, then it comes out to the socket, it is stored once, and you just handle this reference. If the binary is small, then it is created right here in the heap under 64 bytes as 8 words. So you operate it as one value, it is sent and copied as one value. And sometimes you need sub-binary when you do binary colon part, or you match something and you take part of it, then a sub-binary is created, which may refer to a big one, or may refer to a small one. And there is also some special case I did not mention, match context, that one. When you do binary match, it's multiple steps in the virtual machine, so it creates some temporary object called binary match context. It also can refer to heap bin. Why is this important? Is that as long as these values live, this will never be freed. So if your program takes socket data, processes it, sends between processes, and throw it away, this thing may live longer than you want. So you need to remember who's seen this, which process in my program seen this binary. Then you garbage collect here, you garbage collect here, and then it can die. Then your memory consumption will be done. So if you build the binary from multiple appending operations, it can be optimized. But it will check, the compiler will check that you only use it once and you don't share it with anyone. Then it will not recreate binary, not copy it over and over, it will build all in one memory. If you use underscore in binary match, it is smart enough to not copy it anywhere, it will just skip that part. And there is a way, when you compile your program, there is a way to see what's been done to my binary operation. Has it been optimized, or did it produce any warning or so? So there's a way in command line. This is what I just mentioned. When you show a big binary to multiple processes, it will increase the reference count, and it will be held alive as long as all processes who've seen it keep storing it or do not garbage collect. So you want to garbage collect all your processes, and then memory will go down. And when you grow a binary, when you create something, append something, in a loop maybe, or in your program, it will copy every time, like the good old C++ or basic A plus B when you append to strings. So that part is not optimal. If you want to join a few binaries and then send them, use the list of binaries. It is accepted by sockets. They will be happy to send a list of binaries for you. And when you match, again it creates pointer to binary data reference that you want to free, because this will happen because memory will be stored, not free. 2 words about external term format. A virtual machine can encode your data into a binary format that you can write to disk, you can send over network, you can do something, store it or pass to another program for parsing. Also databases that are written in Erlang use it. So React uses it, Venezia uses it, that's disklog. If you use disklog, also uses this format. And what you need to know, that if you store atoms in this format, you store atoms in Venezia, they go into database as strings. So if you have very long atom, you might think, oh, it's an atom, it's probably compact. When you write it to disk, it becomes a string. So if you have long atom times many millions, why are my files so big? Because, well, it's been converted to string. So in memory they are optimal, of course, because virtual machine has special atom type, which is a number, which is super fast and cheap, but on disk they become, and also bits become, ports contain atom, they become bigger, and so one of the tricks you might have seen in some legacy code is to replace your atoms in the data that goes into Erlang database, replace them with numbers. So they have constants that replace atoms, and then the output data will be more compact and small. but people will look at it like, what is this? This is impossible to read. Why did anyone do this? Well, because of memory limitations. They wanted it to be smaller. A few words about exports and imports. These are the things that you do when you write in Erlang. You refer to a function like this, or in Elixir you refer to a function like that. These are special objects in Erlang that you can call, or you can store them and call them later. And internally they are stored like just a box with the module functionality and maybe some extra fields. And if you create a closure, that is a function inside function, and it can see some values from the outside function. That is called the closure. So it's stored in the exactly same way, plus little, a few extra words of the store values you capture. What's bad about them is sending them over network is not safe. They are data, you can encode them and send them. But sending such objects to another node means the other node will receive module functionality and the data you sent. And the function might not exist, or might be old, or might be something you don't want to be, like someone replaced it with something malicious to run for you. So yeah, don't send code between nodes, and as well don't send the function references. Again, floats. If you have the floating point data, it is stored as double. That is 2 words on 32-bit machines, 8 bytes, or 1 word on 64-bit machines, but plus 1 header, because it's a box. A box has a header at your float. If you have an array of 10 million of them, you have 10 million headers and 10 million floats. It's double space consumption. It's not something you want when your memory is limited and your data is big. So you can consider different ways. You can store fixed points, you can store rational fractions. This will be more compact than the float. Or again, that I mentioned before, the small integer, if you have a counter that exceeds the size of a small integer, it becomes big. You will not notice it. Virtual machine handles it transparently, but it will triple in size. So if you have a lot of them, you will notice. A couple of rules when the data is copied. If you have something that is noticeable big size and you want to exchange it between processes, like you have a dictionary, a config file, and you want to send it between processes, you don't have a global config get or set, you need to send something big. It will be copied when you send the message with this information to another process. The entire thing will be copied. If you write something to nets table, the value will be copied in and out. If you spawn a process and pass it some big value, the copy will be given to the process. So this borderline, anything that crosses between your process and adds ports to other processes, they will be copied. Sometimes it's not what you want. Well, it's transparent, you will not notice, but you might notice performance hit, because full copy is expensive. Also, large binaries are not affected because you only exchange references. Large binaries are stored separately. That is safe part. You will enjoy handling large binaries, except when you store too many references and they're not free. But they are efficient, they are fast. So know your data, know your performance, never guess, always look at the numbers. There are ways to print your data structures in a nice way. You know them, of course. There are ways to measure your performance. There are standard tools in Erlang. There are the debugger and profiler. There are 4 or 5 different profilers exist. You can find them on Erlang documentation. So don't trust your guess. Always measure. Measure your memory and measure your performance. When you have something that is slow and you need to make it faster, then always look at disk access first. It's the most expensive part. Then look at database access. But you can believe like socket is fast, it's 1 millisecond, and the database probably is fast. Well, sometimes it's not, because it also will access disk storage. The remote network access is slow. You might be writing to it mounted network volume, and your algorithm may be terrible, or your data structure may be inefficient. So you are copying something, you're iterating over something inefficient. Again, measure, never guess. Don't trust your gut feeling, look at the numbers. And I think that was it. So there is a website that I created with small details. You can visit and have a look. There is the Beam book created by another person that I contributed a bit. And that's me. Thank you.
Thank you very much. Then we'll do like a 5-minute leg stretcher. Fill up beers, visit the loo.